Hi, welcome to the 7th episode of Coding with Amadeusz. Just a moment ago in the previous episode, we connected the range detectors to Raspberry Pi using analog to digital converters. And in this video, we're going to write software which will read measurements. So let's go to Visual Studio and create a new Universal Windows app. It will be a blank app. When we are interfacing with Raspberry Pi, we are primarily interested in two namespaces. It is Windows.Devices.Gpio and Windows.Devices.Spi. However, those namespaces are not available right off the box. So the first thing we need to do is right-click on references of the project, add a reference, and go to Extensions, and hit Windows IoT extensions for Universal Windows Platform. And I'll just pick the one with the highest version number. And now with the reference in place, I believe we should be able to access SPI, that's correct, and GPIO. Okay. The app that reads measurements from the sensor will be very simple. We need to first set up the sensor and then set up a timer which will poll the sensor. So let's write init SPI because we're using SPI interface and init timer. Microsoft released a bunch of IoT samples on GitHub, and I'm adapting a potentiometer sample where a potentiometer is hooked up to Raspberry Pi also through this analog to digital converter, and we're reading the values of this potentiometer. So the first method, init SPI, I have adapted a little bit. So that all we do here is we use the chip select line 0, which corresponds to the line that we use on Raspberry Pi. And we're setting the clock frequency. We're using 500 kilohertz. All we need to do is not exceed 3.6 megahertz. And this information can be found in a datasheet. It says how fast can this analog to digital converter be clocked. Now the mode, SPI mode, mode 0. There are 4 modes. I don't really know what's the difference between them, but for now we'll use mode 0, and if something doesn't work, we'll investigate further. And then later on, the whole goal of this method is to get the ADC, and ADC is an instance of SpiDevice. So I will also copy some fields right here. We'll walk over them in a bit. So after we get the SPI device, we need to set up the timer. Just a dispatcher timer which hits every 100 milliseconds and invokes the timer tick method. Communication using SPI is accomplished with the TransferFullDuplex method on the SPI device. So we'll say ADC.TransferFullDuplex, and this method takes two params, 2 byte arrays. The first one is information that we send to the device, and the second one is the information that we will receive. And first we need to figure out what is the size of those buffers. Here I have the size 3, and now how did I come up with that? The response from the analog to digital converter is 10 bits. And response between 9 and 16 bits can be represented in 2 bytes. And we also need 1 more byte for padding. So we have 3 bytes. That's why our response is 3 bytes. And in SPI communication, for every byte that we want to receive, we need to send 1 byte, which means that we also need to send 3 bytes in a request to the device. The ADC's datasheet will tell us exactly what to send to get the response that we want. So let's go to the datasheet, and here in section 5 there's table 5-2, and it shows us what bits we need to send to invoke certain response. We want to probe channels 0 and channels 1. This is where we connected the distance sensors. So to probe first sensor, we need to send 1, 0, 0, 0. And to probe the second sensor, we need to send 1, 0, 0, 1. So let's jot down this. We need to send 1000. Then when we scroll further in the datasheet, we see that before we actually send those 4 bits, we need to send 1 bit to begin the transmission. So we need to tell the device, hey, let's talk. And that's where this 1 bit comes. And everything before we don't care about, and everything after we don't care about. So we'll just use zeros. So we have the binary representation of what we want to send to get the response from the first sensor. And now for the second sensor, all we need to do is send a 1 here. So this will probe the first sensor, this will probe the second sensor. So now let's convert it to hexadecimal format. To make things easier, I set the byte boundaries here when our information actually changes. So that the first byte, we're just sending 1 to initialize the connection. Then in the second byte, we are sending the data that we need to send. And then in the third byte, we're just sending zeros. This was very confusing to me at first because some tutorials I was working with earlier, they were calling for me to send, for example, 6 or something like that. And the reason they did that is because they never aligned it. Here we're sending 1, 1 followed by 0. So you might as well just say this. And if we want to probe the second channel, we can just say 11001. So you can implement. At first I was very confused about it when I was looking at other tutorials, because they were telling me to use 6 or 7 values that really didn't make any sense, but they worked. So how did they work? Notice that here we just need to send 1100, and for the second sensor we need to send 11001 followed by anything. So you can say that this is 3, this looks like 3. This one looks like 3 followed by an F. So technically, yes, we could say send 30 for the first sensor and send 3F for the second sensor. And this will work. But it's really confusing. So let's see how we can convert this representation to hexadecimal, which all actually makes sense. Each byte is 8 bits, and in hexadecimal, every single character, every single digit is 4 bits. So 1 byte is made up of 2 characters. And we have 0x just to tell the C# compiler that this is a hexadecimal number, so don't worry about 0x. So how do we arrive at 01? A byte is 8 bits. So we need to find 8 bits, and each hexadecimal character corresponds to 4 bits. So we can split our byte stream into groups of 4 for clarity. The first group of 4 corresponds to hexadecimal 0, and the second group of 4 corresponds to hexadecimal 1. Now for the next one, you can either convert it in your head, or you can use the Windows calculator. It's a fairly cool tool. Just switch from scientific view to programmer view, and in binary hit 1000, and it automatically converts it to other format. So in hexadecimal is 8. And then we just follow with zeros. Now for the query for the second sensor, we also start with the 1 at the beginning, but then we have 1001. So we can go back to the calculator and say 1001, and calculator converts it to hexadecimal 9. Alright, we're ready to intercept the data. We want to display the data that we receive in the output window because there's no GUI for this app. So let's say system.diagnostics.debug.writeLine. And we'll just print the elements of the response buffer array. So response buffer, first element, the second element, and the third element. And we'll also take the measurement for the second sensor, so we'll just use the second range query. And the response buffer is the same. Let's debug our app and see how the code behaves. First, in Visual Studio, change the architecture to ARM, and we'll pick remote machine. And in a window right here, you can either choose an auto-detected app or use Windows IoT Core Watcher. The link to it is in the description. Copy the IP address and paste it here. However, make sure that the authentication mode is set to none. But I'll stick with the auto-detected MinWinPC. And we'll hit remote machine again. And now the build starts. It will deploy the code to the Raspberry Pi. And we are using the output window to get the response, and here it is. We see that the data is coming in, and if we do something with the sensors, we see that we can change the way data looks, and if we cover both sensors, we see that both sensors display a 2 here in the middle column. Now just one, now the other one. If something doesn't work for you, try to debug the circuit, and if you have a resistor and an LED, you're set. This LED's shorter leg is connected to the negative rail, to the ground, and the longer leg is connected through the resistor to the distance detector. When this happens, it means that the detector correctly works, and the issue is somewhere in the wiring here or in the code that initializes the SPI connection. However, if you wave the hand over the detector and the LED doesn't work, then your issue is probably in supplying power to the detector. Alright, now let's see how we can improve our results. We're just seeing the byte array. Let's convert it to a human readable number. We are receiving data in response buffer, so let's say var result1 equals convert to int response buffer. We'll generate this method. It returns an integer. And now we're going to do some binary math. I will paste the code from the potentiometer example. And let's try to see what's happening here. So first of all, we are accessing the third element of the data array. So the first assumption is that this array data, it indeed has length of 3 at least. Now we're instantiating the result to 0, and what's happening here? Let's take a look at the data. How does the data look like? We're receiving 3 bytes. Let's say the first byte is AAAA. Now we have Bs. So this is the data that we're receiving. And what is data 1? Data 1 is this. And now when we end it with hexadecimal 3, this is the same as ending it with binary . So it will look kind of like grade school math. What happens when we end something with a 0? We receive a 0. So those things will become a 0. And what happens when we end something with a 1? This, whatever we provided, carries over. So in this operation, we are converting whatever we have received in this byte such that we only see those 2 bits. Then we're shifting this by 8. So after doing this, we end up with that. And when we add the last bit of data, this is what we have. And why do we do it this way? It's because the analog to digital converter that we use has a 10-bit output. So we are interested in only the 10 bits, and whatever was there earlier, we don't care about it. So now that we received the result, let's display it instead of just the raw bytes. And now we'll debug again and see what happens. Okay, we're receiving numbers. It looks like the second number corresponds to the left sensor and the first number corresponds to the right sensor. And we see that there's a bunch of noise. So how about we take this data and put it in Excel to see how it looks like. We just need to add one variable, measurement, which is an integer, and every single time the timer acts, the measurement will be increased by 1. And here we have commas, so we will take this data and put it in a CSV file, which then we can load in Excel and we'll graph it. Okay, here's the data. Let's clear the garbage above, and now let's do some tests. First, this kind of motion. Now let's go a little bit lower. And now even lower. Okay, that should do the trick. Now I'll select everything. We'll copy it. We'll put in a Sublime text, and here we see there is some garbage that we don't need. And it looks good otherwise. Okay, we can insert a row above and say measurement, sensor 1, sensor 2. Now we'll select this data and graph it. So we'll insert a chart. I usually use scatter plots. Now we'll move it up, and here it is. So here is our data. We can see that the noise is in a range of 50, sometimes goes higher to maybe 70, but all legitimate measurements are over 100. So we'll be using this data to create the navigation controller for our smart mirror. And regarding the noise, when we go back to the microcontroller's datasheet, there's a couple paragraphs about noise. Particularly at the bottom, they are saying that we shouldn't be joining the digital ground with the analog ground. Also, the distance between the measurement and the microcontroller should be very small. And here I have connection using 3 wires, so there's definitely a lot of noise, and I'm pretty confident that in a smart mirror, in a final product, the noise will be much smaller. However, for what we need now, we can see that if the measurement is over 100, then it's probably a valid measurement. Alright, so this is our data. We'll be working with that in the next episode. The code for this episode is available on GitHub. The link is in the description below. And if you have any questions, definitely ask them. There is some non-trivial code related to the bits and bytes. So I'll just clean up this code, I'll save it and put it up on GitHub. Cheers, see you in the next episode.